Hello, dear friends and my fellow researchers. I am Samet Fanta, a research scholar from Indian Institute of Technology, Kanpur, and I come from Ethiopia, Defense University College of Engineering. And this is one day online workshop, which is prepared based on the request from my fellow researchers and students of IIT Kanpur, as well as other institutes. So the workshop is prepared by the collaboration of IIT Kanpur Aerospace Engineering Department, particularly structural aerospace structural lab. And my lab mate Sanjay have truly explained the most important preliminary concept of FEM and the interaction of the computer with human being and that GUI, graphic user interface of the computer in the morning session, and how the computer helps us to model finite element problems. And therefore, I will extend my presentation from the point where Mr. Sanjay stopped. For any questions, I will give you a chance at the end of uh, and I will provide my link for further communication. So it is an extension of online workshop on introduction to finite element using Abacus CAE. This is session 2. It is mainly emphasized on impact-induced damage analysis on thin structures, which can be isotropic structures made from isotropic material, or it can be a structure made from composite material. So sorry, let me share screen. So it is an extension of online workshop on introduction to finite element analysis using Abacus CAE. This is session 2, which is mainly emphasized on impact-induced damage analysis on thin structures. Either it can be of metallic material or it can be composite material. So the objective of this presentation is to understand the finite element method modeling, FEM modeling approach for different loading scenarios, to develop a stepwise impact model of thin metallic sheet, either of laminated structure or other metallic structure, which is impacted by a blunt projectile and using Abacus CA to explain the FEM procedures of damage modeling of fiber reinforced polymer composite laminates in Abacus, to generate the Python script while running Abacus file, or to implement the script to Abacus model, and to implement the Fortran developed user material subroutine codes like UMAT and ViewMat codes in Abacus standard or in Abacus explicit. So it is better to start from the basic knowledge of FEM. So what is FEM? So the finite element method is a numerical technique used to perform finite element analysis of any given physical phenomena. It is a numerical, it is necessary to use mathematics to comprehensively understand and to quantify any physical phenomena, such as structural or fluid behavior or thermal transfer or wave propagation and growth of biological cells. Most of these processes are described using partial differential equations. As example, we can take the dynamic equation of the structural dynamics equation, mx dot cx dot plus kx, which is equal to f external. So for a computer to solve these PDEs, numerical techniques have been developed over the last few decades, and one of the most prominent today is the finite element method. So why is finite element is needed? Just implicit versus explicit finite element methods is used to simulate naturally or artificially occurring phenomena. This numerical technique is the foundation of simulation software. In order for the engineers, include aerospace engineers, civil engineers, and as a whole, mechanical engineers, to assess their design for failure and damage in various loading conditions before going to prototyping or implementing stage. Time-dependent versus time-dependent analysis. For all nonlinear and dynamic analysis, incremental load are needed, which are also known as displacement steps. We refer to the problem as time-dependent when the effect of accelerations are pronounced and cannot be neglected. For example, in drop test, the highest force occurs within the first few milliseconds as the item decelerates to stop. In this case, the effect of such deceleration must be accounted for. In contrast to that, when loads are slowly applied onto structure surface, then the loading can be considered static or quasi-static or time-dependent. This is because the loading time is slow enough that acceleration effects are negligible. Implicit versus explicit analysis. All explicit and implicit and explicit problems are expressed using mathematical partial differential equations. While today's computer cannot singly solve PDs, they are equipped to solve matrix equations. This matrix equation can be linear or nonlinear. In most structural programs, the nonlinear equations fall into three categories. These are the material nonlinearity, the geometric nonlinearity, and the boundary nonlinearity. Where in the case of material nonlinearity, where deformations and the strains are very large. For example, we can take the polymer materials like rubbers. And in the case of geometric nonlinearity, strains are small, but rotations are large. For example, the thin structures. And boundary nonlinearity is due to nonlinearity of the boundary conditions. This can be easily expressed in terms of contact problems. When two or more surfaces are in contact, this problem will happen. So when we come to implicit finite element analysis, one method of solving for the unknowns, the unknown variables, is through the matrix inversion. For nonlinear problem, the solution is obtained in a number of steps. And the solution for the current step is based on the solution from the previous step. Okay, so for the large loads, inverting the matrix especially the stiffness matrix, is highly expensive and require advanced iterative solvers and computer higher order computers. This is also known as a backward Euler integration scheme. So these solutions are unconditionally stable and facilitate large step time steps. So despite disadvantage, the implicit method can be extremely time consuming when solving dynamic and nonlinear problems. And there also be a convergence issue, the issue of convergence of the solution. So the implicit method should be used when the events are much slower and the effect of strain rates are minimal. So how we can develop how the Abacus solver designed for implicit dynamic method. The Abacus system is designed with the governing differential equation of this type, that mass times acceleration at I plus 1 times step plus 1 plus alpha ku of ti plus 1 minus alpha ku ti, which is equal to f of ti plus 1 plus alpha delta t. Again, the displacement is expressed as u of ti for I plus 1 times step, ti plus 1, which is equal to u of ti plus u of ti dot ti plus 1 over 2 delta t square as a whole 1 plus 2 beta u dot dot of ti plus 2 beta u dot dot ti plus 1. And the displacement is expressed in as for I plus 1 time, it is equal to u of ti plus delta t as a whole 1 plus gamma times u dot dot ti plus gamma u dot dot ti plus 1. So the Newman functions or the Newman constants alpha, beta, and gamma are expressed as alpha is given as 1 over 3 minus 1 over 3 to 0. Beta is 1 over 4 times 1 minus alpha square. And gamma is 1 over 2, 1 minus 2 alpha. And the initial conditions are specified as u of t naught is equal to u naught, u dot of t naught is equal to u dot of u dot naught, and u dot dot t naught is obtained from the governing differential equations, which is given with strike with value alpha is equal to 0 and I is equals to minus 1. For that, we obtain mu dot dot of t naught is equal to f of t naught. Then this implies that u naught dot dot of t naught, which is equals to m inverse of f of t naught. So this is the explicit algorithm that the computer graphic system or GUI interact with the implicit dynamic modeling procedure. Explicit finite element analysis is also another important. So explicit analysis aims to solve for acceleration, u dot dot. In most cases, the explicit analysis consider lumped mass, and the diagonal, actually the mass matrix is a diagonal lumped mass. So in version of diagonal matrix, mass matrix is straightforward, and it includes inversion of terms on the diagonal only. Once accelerations are calculated at the nth step, then the velocity will be calculated at n plus 1 over 2 step, and the displacement in n plus 1 step. In this calculation, the scheme is not conditionally stable, like as in the case of implicit case. And smaller time steps are required. That small time discretizations are required. To be more precise, the time steps in explicit finite element analysis must be less than the current time step. That means the time taken by the sound wave to travel across an element. So the explicit method should be used when the strain rates or velocity is higher. Let's see how the explicit scheme is designed. So to explain the dynamic explicit analysis scheme in Abacus FEM tool, let's take the schematic of dynamic system, which consists of mass, the dashpot, and the stiffness, which is subjected to an external force f of x with an initial displacement u, with initial velocity u dot naught, and the governing differential equation is given as m matrix of m times u dot dot plus c times u dot plus k times u, which is equal to f external. And then now just plotting the u versus t graph on that, we can apply the central difference method for the steps, starting from I minus 1 over 2, I plus 1 over 2, and I plus 1 within this interval. So the interval is from I minus 1 to I plus 1 is delta 2 times delta t. And then taking the u values for I minus 1, for I minus 1 over 2, for I plus 1 over 4 I plus 1, and then manipulating it for displacement. For example, ui minus 1 over 2, u dot I plus 1, which is equal to ui minus minus 1 over delta t. Again, for ui minus 1 over 2, which is equal to ui plus 1 minus ui over delta t. Now, the equilibrium equation at I is derived as ui dot, which is equals to ui plus 1 minus ui minus 1 over 2 times delta t. And the acceleration ui dot dot is equals to ui dot I plus 1 over 2 minus ui dot I minus 1 over 2 over delta t. And combining these equations, finally we can get ui dot dot, which is equals to ui plus 1 minus 2 times ui plus ui minus 1 over delta t square. Now, substituting these equations into the governing differential equation, we can get m times ui dot dot. Instead of ui dot dot, we include these equations. C times ui dot equation, and k times ui, which is equal to f external. And making some rearrangement on that, finally what we can get is equals to ui plus 1 ki, which is equal to f external minus f calculated f here. And then just neglecting the stiffness terms, finally what we can get is this equation, that ki is equals to m over delta t square plus 1, c over 2 delta c. So let's neglect the stiffness term. So this is brief steps of those equations. Okay, so ui dot tn is given in this format. So neglecting the higher order terms, and converging errors to the second order for time step delta t approach to 0. We have m times u naught dot u dot tn, which is equal to ftn minus kutn. So ftn is the external force, and the displays are the velocity u dot tn plus 1 over 2, which is equal to u dot tn plus 1 minus 1 over 2 plus delta t u dot tn. And then finally the displacement in the n plus 1 time step, which is equal to u times tn plus delta t u dot tn minus 1 over 2. And applying the boundary conditions of the initial condition u of t naught, which is equal to u naught, and the u dot of t naught minus 1 over 2, which is equal to u naught dot. So this is the working principle of explicit dynamic methods in the Abacus dynamic solver. Now let's come to modeling for a particular purpose, or let's come to model the impact problem. For that, modeling foreign object impact on laminated thin structure using Abacus. So for the practical purpose, we have to start with some physical problem domain and follow stepwise procedure to understand the concept. The model contains rectangular thin laminated plate of standard LCPM standard size with a thickness of 2 millimeter and is impacted by a rigid tool dropped during maintenance operation with mass 2.2 kg and some diameter 5/16. The part contains lamina of 0 and 90 and the interface, and also impactor are to be modeled using Abacus CAE. The plate is considered deformable and stacked in such a way that 090s, and this needs some knowledge of Abacus, and the composite material knowledge is also mandatory. So let's start all our work with some Abacus model. So let me open the Abacus. So until it open, let me go to our discussion. Okay. So the preliminary step while we are starting Abacus CAE is we have to open Abacus CAE from our start session. We have to set the directory to save all our work, save it with some name, and to generate Python script, we have to go to File, Micromanager, Create, and give some the script name as impact. Then to model the part and to run simulation in Abacus CAE, we can use either work with various modules in the drop-down menu or using workflow trees. So how we can do these things, let's see. So Abacus is opening. So this is the Abacus screen. So we start with standard explicit method. Okay, so On this, we start with creating some folder, on some particular file and set work directory. Okay, let me go to somewhere in my computer. Okay, so let me impact problem. Okay, now let me save this thing, save as Abacus workshop. Okay, with the name impact simulation. Okay, so on that particular folder or impact problem, Abacus simulation file is saved, and once I save it, I immediately start with a running script. So for that file, micromanager. So let me call it as create impact. Okay, then say continue. Then the recording will micro will start to record. And if we don't want to continue it, we will stop it. We're using stop recording. So it will continue to record all what we are doing. Then let's go back to our work. Okay, so the next is we can work with the module or work with other Abacus this tree structure, work tree structure or module. So we have different modules in Abacus. These are part module, property module, assembly module, step module, interaction module, load module, mesh, optimization, job, visualization, sketch, and so on. So this each module have its own particular use. So the part module helps to contain all the geometric entities. It contains all geometric entities and enables us to sketch the part and create the part. Again, to dimension the part. The property module helps to create and assign materials, properties, and sections. And also, assembly module helps us to assemble all components under analysis. Step module identifies the analysis step to introduce the required analysis output. And so, interaction module provides interaction and constraints between parts in assembly. And the load module helps to create initial conditions, boundary conditions, and the load. And the mesh module to assign the finite element mesh and the elements. And job to run the job and to monitor it while running. And finally, the visualization module helps to visualize and extract the analysis output. So let's go to creating part. That is our major concern. So we have to create two plies with 0 and 90 name and interface layer with name interface. And we have to create also the another impactor. So the plies are created with size 150 millimeter by 100 with 0.25 millimeter. And interface is 0.02 millimeter size. So let's go to the Abacus model. So I'm going to create it very fast. Okay. Here, click on create part, extrude. Okay, 3D deformable, extrude. Continue. On this, let's create rectangle, and let's give dimension, that is 150 millimeter, and this dimension is 100 millimeter. So let's see by zooming in. So it is so let me bring it to it is center to 0, position. So for that, let me move it. Okay, move, only move, not copy. And then from this point to 0, 0. Yeah, done. Now let's extrude it with the thickness. Done. Extrude to 0.5. Let me use 0.5 millimeter for the time being, E-3. So this is the plate. And then second plate is having the same dimensions except the orientation, so that I'll rename this as 0 ply, and let me copy it with name 90. And if we want to include the interface line, we can copy it. We can copy this, and we can reduce the thickness to give name interface. And let's reduce the dimension of, because interface layer is very thin layer, which help us to analyze the delamination case. So that let give 0.005 millimeter. Okay, so we can see it's very small interface layer compared to with ply, which is situated between the plies. Now the remaining thing is creating the impactor. So impactor is discrete rigid impactor, shell revolution. Okay, continue. Okay, then create a circle and give dimension to the circle. And the dimension is 8 millimeter. So then 1/4 of the model is sufficient. And we can trim the remaining portion. Yeah, so that is the 1/4 of the and then revolve it to 360. Then we can see the impactor. So let's assign this rigid impactor needs reference surface or reference point. So let me provide a tool reference. So considering this point at the center of mass center of the object, and then now we can go to the next module, because in part module we created all important geometries here. Okay, so what we created are 0, 90 interface, and this, let me rename this as rename it as impactor. Okay, so we created 0, 90 interface and impactor. So Rob, I am trying, just I will call you later. Later, with you later. Okay, I will call you. I will call you. Okay. Okay. So sorry for interruption. Impactor interface 90 are created. So the next is the property module. So in property module, we have to assign all important properties. Property for individual place, property for the impactor, property for the interface. That can be done separately. So let's assign property for the impactor first. So impactor is a rigid body, so that we have to give some reference set. So let's create a set called ref, okay, with the predefined reference point, okay. Then and then the only required property for impactor is the mass only. So for that special, okay, so it's a special inertia create point mass, then give this location for the point mass and give the isotropic mass of 2 kg. Okay, the unit system which I am using is metric unit system, so there is no confusion on that. So this green color indicates that the assigned mass, and then the remaining other, for example, this 0 and 90 interface needs a separate material. So I'm going to generate material for that. Okay, material name, let it be lamina. So density for lamina, let 1600. Let's go to mechanical elasticity, elastic. For lamina, there are many material types available here, but we are going to use the laminar property. Okay, so this laminar property includes E1 that 135.30 E9 gigapascal, 10.3 gigapascal, 0.32, and this is 4.8 gigapascal, 4.8 gigapascal, and this is 3.7 gigapascal. Okay, then we have to give the damage for fiber reinforced composite. So we'll discuss on this issue later in our slides, that how this damage for fiber reinforced polymer composite will implemented. So hashing damage. So on that, longitudinal tensile strengths, longitudinal compressive strengths, transverse tensile, transverse compression, longitudinal shear, transverse shear. These 6 properties should be assigned. So let it be 2800 megapascal E6, 1250 E6 megapascal, 42 E6, 235 E6, and shear 80 E6, and let this be 70 E6. These are the strengths data, and let's give alpha value 1, Okay, and go to sub option damage evolution. So in damage evolution, we can see energy type linear, okay, with longitudinal tensile fracture energy, longitudinal compressive fracture energy, transverse tensile fracture energy, transverse compressive fracture energy that are gamma 11, gamma 1, gamma 11T, gamma 11C, gamma 22 T, gamma 22 CR should be assigned. So this is 130 E3. This is 40 E3. This is 0.2 E3 and 2.1 E3. Okay, so these properties are for lamina. So once we create laminar property, let's assign this property to the lamina. Okay. So how we can create? We have to go. We can use create composite layup option, or here a composite option. Okay, create conventional continuum shell. There is an option conventional, continuum, solid. So many options are there. So let's use continuum shell, continue, and then no, okay, composite, create initial ply count, let it be 1 only, because I am going to assign 1 to 1 plies, continue. So the first ply is 0. Let's give ply name 0. The region of the ply is this one. Okay. Material is the laminar material. Okay. And the relative thickness is 0. Okay. 5e minus 3. Rotation angle is 0, and integration point is 3. Then it is okay. So immediately that 0 ply shows material property assigned to it. And the next is 90 ply. Okay, for 90 ply also we can do the same thing. Create, okay, continuum shell, and give name 90. And region is this. Material is the laminar material, and relative thickness 0.3. Okay, angle is 90. Then integration point 3 by default. So 90 ply also assigned material, and what we have left is the interface. So the interface also should be assigned with material. We have to provide the interface properties. All these properties are there in my slide, so we can see the slide first. What are those material properties? Let's see from this slide. We already created the impactor reference point. The impactor is already generated or created. Okay, so the mass of impactor is already assigned. Okay, and then the property module, in the property module, I assigned all these elastic properties, strength properties, fracture property of the composite for T700S M21 material. Okay, so this is from some reference. I took it from experimentally done work by Toulouse University It is a French university actually. And then the interface properties are also given here. The finite stiffness coefficient are there. Interlaminar fracture toughness for interface are there. Interlaminar alloy strengths of interface are there. So this should be assigned to cohesive interface. So how can I? So let's go delete the name interface. Interface or cohesive. We can call it as cohesive. Okay. Density, which is 1280 or 1300, 1300. Then mechanical elasticity. Okay, elastic, that the material property is traction, that uncoupled tractions are there and coupled traction is there. So we select the uncoupled traction, which is this one. So we can provide the material property, penalty stiffness. These uncoupled tractions are of the finality stiffness property of cohesive layer. We can apply these values. So that is 1 is 6 in Newton per millimeter cube. That means it should be 10 E 15. 10 E 15. 10 E 15. So for this, many researchers use some empirical relations with other properties. Turon discussed, Turon et al. Discussed or investigated some formula for this. That penalty stiffness of the first one, K11 is equals to alpha times E3 over smallest thickness is developed, and then we can go to damage for traction separation law, and that is quadratic damage initiation criteria is considered. For that, nominal stress normal only, nominal stress first direction, nominal stress second direction should be assigned, which are Tn, Ts, and Tt, that internal level strengths, 60, 80, and 70. Let me give them 60 E6, 80 E6, 70 E6. And then go to the sub options, damage evolution. So the interlaminar damage evolution is considered either displacement or energy based. So let's consider the energy based type energy, linear softening. We have linear, exponential, or tabular softenings are there. So let's take linear. We'll discuss on this all issues. Degradation maximal. There is an option multiplicative, so maximum let's take, and the mixed mode behavior should be mode independent, tabular, power law, BK. These four options are there. Let's take power law or BK. That is that. We'll see it. Okay. Clearly, I will define them, and then let's go to the fracture energy, the interface fracture energy, that critical energy release rate, GC1, GC2, GC3. So GC1, let it be 0. Let it is given 0.21 E3. This one is 2.1 E3, 2.1 E3. Okay. So these are the interface properties. Okay, so now let us assign these interface properties to the interface layer. For that, how we can assign create section. Okay. Here there is no option for cohesive layer, so let's go for others. Then we can find here cohesive. Then on the cohesive material type, select the cohesive, and the response is traction separation response. Okay, so we can take the remaining as it. Okay, and then assign the section. Okay, so that is section 1. Okay, so the cohesive section also assigned. Yeah, so before I leave this module, let us discuss what I have done and included there. So these are the material properties which are taken from experimental data from different authors, and these are also the same. And then what the damage initiation criteria are. I introduced the Hessian damage initiation criteria. So that means in Abacus built-in, this damage initiation criteria, which refers the onset of damage of stiffness at material point. So in Abacus, damage initiation criteria for fiber reinforced composites are based on Hessian theories, which developed in 1973 and in 1980. So it is primarily intended for the use of with fiber reinforced composites and takes into account 4 failure modes. One is fiber tension damage, which is when stress 1 and greater than or equal to 0. Then this equation holds true. That xt and tensile strength in longitudinal direction, tensile shear, longitudinal shear are introduced here. And the alpha is the another parameter, which value is 0 in the case of 1973 and 1 in the case of 1981. Another fiber compression, matrix tension, matrix compression. These 4 are considered in Hessian's criteria. So this is the Hessian 2D criteria actually. Okay, this is Hessian 2D criteria, and it will extend it for the Hessian 3D criteria. So how we can implement these things? So in already, as you have seen, mechanical damage for fiber reinforced Hessian damage, then alpha is equal to 0 to use the 1973 and alpha is equal to 1 1980 model. So alpha is the coefficient to determine the contribution of shear stress to the fiber tensile initiation criteria. Okay, so the parameters xt, xc, yt, yc, SL, ST are already the parameters of the strengths which we implemented to our case. And the sigma 1, sigma 2, and the tau 1, 2 are the effective stress tensors or components. So the effective stress tensors are used to evaluate initiation criteria and compute sigma is equal to CD E. So E is the strain, CD is the damage elastic matrix, which is given as this, and here D is the okay. Yeah, that D is the delta, which is represented with different parameter, and yeah, where DF, DM, and DS are the internal variables or damage or that characterize fiber, matrix, and shear damage, which are derived from damage variable DTF, DCF. So DF is this. When it is DF when damage variable of fiber tensile is when DF is equal to df of t if sigma 1 is greater than 1. df is equal to dfc for the compressive case if sigma 1 or less than 1. In the case of matrix, dm is equal to dm of t if sigma 2 to greater than 1. dm is equal to dm of c if sigma 2 to less than 1. So the damage variables versus equivalent displacement are plotted in this. At the very beginning, if there is no damage, the damage variables are 0. And when maximum damage occurs, the damage variable is equal to 1. So this implies the and the shear damage is combination of the matrix and fiber damage. Okay. The damage evolution, the procedure will include data entry of damage evaluation in the property module. When you create damage initiation criteria, select sub option, displacement or energy. Select the type of damage evolutions, displacement of energy. Again, select the softening method, linear, exponential, tabular. So linear softening method, which characterize this traction separation graph. And the graph of this line indicates the initial stiffness, effective stiffness of the material until the material damage initiation. Once the damage initiation reaches to 1, then the elastic limit damage occurs at delta is equal to delta node. So this is the point where damage initiation occurs. Then the material starts to degrade its stiffness in this round. And the area under the curve is called the energy GC, which is the critical energy. Okay, so linear and exponential damage evolution. Selection of mixed mode behavior for material associated with cohesive. So mode independent, tabular, power law, and BK are the options. So the power law is related with this equation, that is GI over GIC. GIC is the critical energy release rate. Okay, so GI is the energy release rate, but GIC is the critical energy release rate in the first normal mode, in first shear mode, in the second shear mode, and so alpha is the power law coefficient, which is 1 to 2. Okay, and then that BK criteria is characterized with this equation, and the BK coefficient or the BK coefficient is obtained from the experimental result. Select the degradation. So maximum degradation or multiplicative. So by default, maximum degradation is selected. And select the mode mix ratio for the cohesive element. So if it is energy based mode mixity, then we have this equation. And if it is traction type, then the traction mix mode ratio is used. For the Hessian damage evolution model, the data table contains this thing, that fracture energy, GFT, GFC, GMT, GMC. So that are already what we have introduced. We assign the material properties and the sections already, as we have seen. And the next is the assembly module. So in assembly module, we can assemble the zero lines, the interfaces, the impactor together. So how we can make them practically? So for that, let me go to the Abacus model. This is the model. So on this, let me switch it to Abacus, assembly module. In assembly module, create instance. We can see in this impactor interface 90, 0. So our arrangement is 0, 90. 90, 0. So that contains 4 plies. Now for our simple modeling with time, I can, okay, let me 90. I can model only 190 and 10 is one interface only because of time constraints. Let 0 apply. Make sure that this out of offset is on. Now interface, apply 90, apply impactor. Okay, so I'm not fully taking all the plies because of time constraint. So let me use only this plies 090. Okay. So now let's assemble them. Move this layer. Okay, let me move it from this point. Okay, 0 interface 90. Yes. Now these are 0 interface 90 layers, and let me bring the impactor to this position. To 0, 0 position. Okay, so now impactor is also here. So we have to make some rotations and translation motions. And let's rotate the impactor. Okay. Start point. Okay, 90-degree rotation. Let me check 90 degree. Yeah, that's correct. So the impactor is rotated and positioned in proper position. Okay. Yeah, this is the impactor, the plate assembly. So assembly is done. If we need to assemble more and more plies, we can add 2 more actually. Let me make it 0, 90, 0 ply. So let me add 1 interface and 1 0 ply to make it realistic. So let 1 interface apply and 1 0 ply. So this computation is 0, 90, 0. Okay. So let me bring this thing. Okay, move. I want to include it here. Okay. So now we can see 0, 90, 0, 0 interface, 90 interface, 0. So this is a stack of layers. So assembly is done now. So what is the next? The next is a step model. So that step model is the model in which we can assign the simulation time. We can request for output, analysis output. So, so let's revise the assembly. So we already done the assembly. Okay, so the next is step model. So step model helps us to specify the time of simulation, as well as various options defining the finite element algorithms that were either explicit or implicit analysis algorithm also defined here. And then it is also used to define variables that will be saved to the output database during analysis. Okay, so for that, we go to step, create step, dynamic explicit, and the procedure as general type, and time of impact process at 0.6 millisecond. So let me, so here, create step, okay, create step, you can say impact step. And here, the procedure is general procedure. And sometimes we can use linear perturbation, but general procedures is there. By default, it comes with static general analysis. So I need dynamic explicit analysis. We have also implicit analysis. Actually, dynamic explicit analysis is there. We already discussed it at the very beginning. Okay, continue. And provide the time period as 0.006, so that's 6 millisecond, and make sure that NL geom is on. Okay, so the next is we have different outputs here, create field output and history output, so that we can fill them later. After creating the interaction, we will come back to make it. So let's go to interaction. Interaction is another model, the module, which helps us to define interaction between laminate and interface, and the interaction between the top ply and the impactor, or the surface under interaction. So for that, let's define the, let's create interaction. Okay, general contact for explicit, and then create interaction property that contact, just continue, mechanical tangential behavior, okay, penalty friction with friction coefficient of 0.3. Again, normal, that hard contact with which with allowing separation after contact is highlighted, and then okay. And also let's create some fake contact. Okay. So let's come out from here. And then let me bring this impactor somehow some height above from the plate surface. Let me move it up. Okay, from it is 0, 0 position to some minus 1, okay, 0.0001, 01. That means in the positive z direction, because positive z is upward. So 0.0001 difference. Okay, yeah. So impactor is in some gap with. Okay, let's go to the interaction model. So let's click on this, then contact pairs. Okay, find contact pairs. Find contact pairs. So we can see, okay, how much parts are there? 5 parts. So the contacts are no, that is not correct. That is not correct. So let me make first. Okay, this is still not correct. Interaction. Okay, how impactor is interacted with others. Okay. Okay, let me move impactor back somehow. Still. Okay. Zero. Okay. Impactor is there. Yeah. 0.001. Okay. Interaction. So let's see. Find contact pairs. Yeah, it should be 4 contact because the contacts are 4 there. We are not including the contact between top fly and the impactor, so that it is 4. And the type of contact should be tie constraint. So all the plies and the interface are in tie constraint. That is done. And let's make interaction between the impactor and the top of fly. So for that, let me separately generate surface to surface contact. Okay. Let this surface as the first surface, the brown color. And next, this top surface of the plate as another surface under interaction, and with a finite sliding approach. Okay. And then the interaction as tangential behavior as frictionless, and normal behavior as hard contact is yeah, done. Okay. So the interaction is made. The interaction between the plate and the impactor is made. So what is next? Now we have to go back to the step module to include the outputs. Okay, so here, okay, output 2. This is field output. So we have some set. Okay, for some set. Okay, that not history. Okay, the whole model. So let me include the energy because we have the hashing damage is implemented, so that we must request for the damage in this case. So damage initiation criteria, okay, should be highlighted. Okay, then it contains all the hashing damage criteria. Okay, this tensile damage, fiber tensile damage, matrix, fiber compressive matrix tensile, matrix compressive damage, damage initiation criteria. We included the interface layer for delamination analysis, so we must include this quadratic damage initiation criteria. Okay, that, and then status should be on. Okay, again here, let's create energy. Okay, history output. Let's go to history output. Through the defined set, we define some set as ref. So on that, we need to have u3, again b3. Okay, okay, r3 reaction. R3. Okay. We have to define these parameters. Okay. So another one is the contact output. So how we can do that? Okay, so it should be on this output, not here. Let me find it here. Okay, interaction. Yeah, for this interaction, the contact force Fn3. Okay. And the contact area should be requested. So this is sufficient for the time being. And then load module will come. So we have to go to the load module. So what we have done, let's see here. On the step module, we assign a dynamic explicit procedure, 0.006 second. We requested U3, B3, and RF3 through the reference point. Okay. We created history output and field output in both cases. Okay, and we requested for the damage initiation criteria. These are required for the fiber reinforced composite. We requested for the traction separation requests for the interface damage initiation criteria. And we define the contact behaviors. Here, contact properties are defined. Okay. We have left something on the contact which I missed. So let me go to this part. Okay, creating constraints to the rigid body. So our impactor is a rigid body, so constraints are required. Okay, so rigid body, continue, that is body element, select the impactor. Okay, then and through this point. Okay, so that rigid body is also created. Okay, then the next is creating load or boundary conditions. Okay, load and boundary conditions are required. For that, let's make it practical. Okay, practically apply the load and the boundary condition here. Yeah, so let's go to load. Sorry, and then click on create boundary condition. Symmetric, axisymmetric, and caster is there, mechanical. Good. So we can select this edge, or we can select the okay. Let me select only the edge. Okay, this edge, the 4 edges of the plate. Okay, 4 edges are selected. Then pinned boundary condition, which substitutes the experimental clamping of the structure. So another boundary condition required is the displacement boundary condition of the impactor. So impactor is allowed only to move in Z direction, so that we have to give the Z motion only, that translational Z motion. So, okay, now let me select this point of the impactor and give only U3 only left, the remaining one 0. So we fix it the U motion only, U3 motion or Z motion only. The remaining motions are constrained. And then the next is providing the velocity to the impactor. So impactor is characterized by the velocity of impact, in the initial velocity of impactor, the mass of impactor. So they provide the impactor motion from the initial mechanical velocity through the same point there. Okay, through this point, less velocity of 2 meters per second. Okay. The velocity is not specified in our program, so let's take 2 meters per second low speed. Okay, now I made mistake. That is, I defined the velocity in predefined field at V1, but it should be on Z. So let it be on Z. So again, I made mistake that it is projected outward rather than towards to the plate itself. So it should be with minus sign. Yeah, you can see it is pointing towards to the plate surface. So that's why we call it as normal impact. Okay. So now the load and the boundary condition is already created. We can see them here. Okay. So what is the next? The next is this is the mesh. Now what we have left is meshing the body. Okay. So load and the boundary is already done. Okay. We have provided the motion constraint for the vector. We have provided boundaries. So once after that, the next step is going to generate the finite element mesh. So how we can create finite element mesh? Let's go to Waka's work. So we are in now mesh model. In mesh model, we can assign the mesh part by part, as well as we can also assign mesh as a whole by selecting dependent or independent mesh. Anyways, in this case, we cannot. Why? Because dependent part instance cannot be edited or assigned mesh because we created it as dependent mesh. Dependent. So now give a global seed from here, seed part. Okay, so the maximum duration. Okay, this thing is not showing. Okay, the seed part size 0 point. Okay, let it be 2 millimeter. Okay, 2 millimeter is too much dense. Let it be 3 millimeter. Okay, so let's mesh it. This is the mesh for 90 also. 0.003. Okay, mesh it. Again 0, 0. Okay, let's give seed 0.003. So let's mesh it. Yeah, and the impactor also should be meshed because this is rigid body is reference node, so it has to be meshed. And now here we have another duties than meshing only. So we have to select the whether the analysis is standard or explicit. The identification will be here. So our analysis is considered as explicit analysis. By default, our case will remain the analysis as a standard analysis, so that we have to change that. In addition, the material type will be assigned here. How we can do that? For example, interface material is a cohesive material. For that, I have to assign cohesive property. So assign material, then click on this, and then we can see here a standard explicit. So it has to be not standard but explicit, and the material type is cohesive. Okay, and element deletion or degradation, we can take default or we can make element deletion. Once the element is damaged, and it will be deleted. So element deletion is selected, so that we selected Co3D8. That means an 8-node 3-dimensional cohesive element is created now in explicit analysis. Okay, so that is hexa type linear mesh type. Okay, again for 90 ply, we have to also do the same thing, but this 90 ply is continuum shell element, and the analysis is explicit, and it is continuum shell element with linear geometric order and enhanced hourglass controlling to control the spurious deformation of the structure. And these are selected. Then finally, we can get C38R, an 8-node quadrilateral in plane general purpose continuum shell, reduced integration with Hauer control, finite strain element is selected. So then we can the same thing for 0, 0. Laminar is 0. Orientation also will be assigned the same material. Okay, explicit, continuum shell, enhanced control. Okay. Yeah. That's assigned for 0 as well as for 90. So now our model is ready to run. Okay, our model is ready to run because all important steps are done. The remaining thing is only running the model and extracting the output from the model. But this may take sometimes and cannot easily display as the result. Due to that, I selected, I already place some output results of some other simulation that is similar simulations, so that I'll show you those things. Okay, these are what I have done. Okay, now let's go to the running the job. So before running this job, I have to stop the micro, which is running yet. Why? Because I initially ran the micromanager to generate fighter script in our code for further study, so that I have to stop that. So let me go to workers and let me stop the micro running. So here I'm going to stop it. Okay, recording micros with the name impact is going on, so that I'm going to stop it. Now the micro is already here, it is run, and we can run it for further. Okay, now let me go to the job module. Okay, so on job module, what can I do? Job, create job. If this is create job, give some job name, as I explained at the very beginning, impact simulation. Impact simulation and the job name. Okay, continue. Okay, but at this point, if our material is user-defined material subroutine, we have to specify this user subroutine for implementing the UMAT or VMAT code. We'll click on that and we can implement it. How we can do? We can see at the last, after finishing this job, I will show you this step. Okay, now the impact simulation job is ready to run. So what I can do? Submitting the job. I have to submit. I have to click on submit. Then the job will be submitted and running, and it will take sometimes. Sometimes means maybe depends on our computer capacity and also memory capacity. So now it is running. You see, it is running. So while we are running, we can monitor our work, and we can check whether the running is properly going or not. So click on monitor and then see different situations. For example, here error is there. The power is not specified, or the specified value is equal to or smaller than 0. This is not allowed in the abacus. So this shows that I made mistake. Why? I used the BK criteria, the power law BK criteria, and I didn't submit the BK exponent to the system, so that it is telling me that I made mistake in my work. So I have to go back to property. And then in the cohesive, let me edit. Here in the damage evaluation, I used BK criteria, but the power is not specified. I have to give this power. That 1.47, most experimental work people found 1.545 or 547, like that. So, okay. So it gives such warning that error warnings will come. So I have to rerun after arranging or after checking. We have to rerun. So let me submit again. Again, if there is any mistake in my procedures which I followed, the abacus will not continue to run. It immediately fails and abort. So what's going on? Let me monitor what I'm doing. Monitor. Okay. There is no error message, but there are a number of warnings that those warnings are not such harmful. Okay. So let's come to, until it is going to run, let's come to our discussion. Okay, so finally, I submitted already the job with the name impact simulation, and I found some error. Okay, that errors will help us to correct the thing, and there are some harmless messages. Okay, so now I try to monitor my work. Okay, so let's come to some important files that generated in Abacus CAE. While we are running Abacus CAE, many type of file extensions are generated on the particular folder or the predefined paths of our saved file. Among them, the imp file is the one which is already there. So it is an ASCII file, and that defines the finite element simulation. So we can separately keep the ink file, and we can also rerun the whatever we have done. This is how Abacus CAE works. Graphic user interface communicates with the Abacus FE platform. So for that, I have one file which is with Python script imp file and also UMAT file. So I can run that file after this. And also another files .log file is also there, which summarizes the outcome of the phase of analysis. The start file is also there, the dot file, the message file, the ODB files, which are very important files of Abacus. Okay, so later we can see how we can implement the UMAP file, how we can implement the Python script, how we can implement the .inp file to remodel for further uh, analysis. Okay. So now visualization will come that extracting the result is the last step. So once the job was completed successfully, you will need to load output data by using file open, then navigate simulation. You can explore the result of simulation like bonuses, counter plots, and also we can animate the result. And if you would like to plot contours of variable, so you can go to result float out field output. If you don't see the variables that you want, the plot that usually means Abacus didn't have it to the ODB. That means you didn't select it proper output at the step module. So you have to go back and select the output. Some additional features of the viewport can be used that we can change different options, graphic options, annotation options. The text file visibilities can be arranged. Graphic options will help us to view good graphic visualization. And Abacus can also plot graphics showing spatial or temporal variations of quantity of interest. So, for example, a plot of contact force, a plot of contact areas. Okay, these are also included. So Abacus C also allows you to post-process the data. For example, you can save the contact force history to dataset using tool XY dataset, create, then select ODB history from the XY data menu. In practice, it is usually easier to post-process ODB data by writing Python script that will ready and modify data extracted from the ODB files. So you can also plot the velocity, displacement, and other parameters which are already created. So based on that, I plotted for two type of run, one for composite plate and another for aluminum plate. So both of them are the same, having the same thickness, but we can see very different visualization of the outputs. Okay, so these are the displacement output for composite. Both are for composite, and these are for aluminum. This is for composite, that is trace 1-1 for composite, and this is trace 1-1 for aluminum. And their value also very different, but their impact is the same energy, having the same thickness, only material difference is there. This is S22 float of the two materials. And this is the Hashim damage criteria for the composite plate. Okay, this criteria is not in aluminum, so that it is not come here for comparison. Okay, these are the history outputs, the displacement, the kinetic energy, the velocity history outputs, the contact force, the contact area history outputs, and so on. So this is all about. Really thanks all of you for your patience. And I will try to run the Abacus imp file and how to implement UMAT file. Okay, and how these UMAT files are created in Abacus. So let's see that. Okay, for that I will stop the running file. This file is running according to the requirement, but I'll run another file on my computer, so the computer will not allow me to uh, go another model on this. Maybe let me try whether it crash or not. I'm not sure. So please be patient. Yeah, okay. So let me run the imp file, which is already free. I created it before. Okay. So for that file, import model, and this model is there in my E. So UMAP Python and imp file for 15 degrees is the one. So let me click on this and you can see. So let me change this thing to INP form. Yeah. So this is the INP file. Yeah. This is file with extension .inp. So let me select that. This is the file is INP extension. Then let me run the Python script already created for this purpose. Still file run script. Let's go to the same place. Here, the py extension file is Python is there. So let's run it. So the Python script is running. So as soon as the Python script run, the appearance of the model is changed. So, and then how we can implement this is every geometries, materials, and other role parameters are done for this. I'm not going to do anything on that. I directly go to job model. Okay, job. create job. Okay, so let me give the job name some actually, okay, job name is some UMAT. Let me say UMAT. Continue. Now, in the case of continuum shell element, I directly clicked on OK. But here I have to click on General and go to User Subroutine file. I click on User Subroutine file, and I have a UMAT code which is generated there in the work directory. Okay, so that work directory is here in the same directory. Yeah, this is Shin failure criteria dot but it is there here. So dot py. This dot py no dot not dot py but dot f. That f implies the Fortran. Okay. 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 User subroutine file not must have a or 4. Okay. It needs some for extension because it is because of my system, but the system with proper Intel Fortran compiler, they can work with simply dot f extension. So for that reason, let me sorry, my computer's very slow. Okay. Okay, this is our file here. This let me really rename it is. Okay, rename is dot 4. Okay. Okay. So now I can implement it. UMAT. Okay, general here, PY. Okay. So now it is also ready to run with okay, job UMAT is ready to run, but I have no Fortran compiler in my computer, so it will not run this computer. But for those who have Intel Fortran compiler in their computer, these UMAT and VMAT codes are easily runnable. So let's come to the model itself. What is there? Here, other than giving the laminar property, the properties are given through, the properties are cohesive properties are given through user material. So here, general user material. So this user material subroutine helps us to provide the material property. all the material properties of the composites are given here. Okay, for example, the youngest modulus of in one direction, two direction. Okay, shear modulus, the Poisson ratio. Other all parameters are given here. Okay, so it is given through the user material rather directly going to mechanical, elasticity, elastic, and composite. And deep variable, solution dependent state variables are stated here. So this is a difference between the implementing materials using user material subroutine and a direct built-in Bacchus implementation. Yeah, so this is all about. I'm really thanks all. Thank you, everyone. This is uh, what I have. Okay, thank you. Okay, stop sharing. And